Hello friends, welcome back my YouTube channel MS Maths. In this video, we'll discuss about Lebesgue measure. So in the previous videos, we have discussed about that Borel set and what is the Lebesgue measurable set that we have already discussed, the sigma algebra sets and Borel sets. Now we'll discuss the Lebesgue measure. So what is the definition of Lebesgue measure? Is basically the if m star, or basically m star is denoted by, for the like notation for the measure, that is basically the outer measure or inner measure. So m star is pr, or r is a real number, to r star, where r star is what? R union of minus infinity to infinity a set. It means r together with minus infinity to infinity be a set. It means it is a whole r, be the outer measure. Okay, it is a outer measure. Then capital M or script M be the set of all measurable set in R. Then the set, then the set function from M to R is defined as measurable set, or the measure of E is nothing but outer measure. It means for each M which is a subset of script M is called the Lebesgue measure. It means if we will apply the measure on a subset of M, it will be equal to the outer measure of that subset. Okay, remark, the outer measure is defined for every subset of R, but Lebesgue measure is defined for the measure set in the R. It means outer measure is defined for every subset, but Lebesgue measure defined for only for those set which is measure in that set, or which subset that are basically the which subset that are basically the measurable set in the real number. Okay, so this is the basically the most important difference between the Lebesgue measure and just outer measure. Okay, there is a theorem is basically they prove that if En be a sequence of Lebesgue measure, if it is a sequence of Lebesgue measure, then we'll prove these two results. So how can we prove? Proceed forward with these results. It's what the measure of union I is equals to 1 to infinite of all ei, which are the subsets of real number, and less than, it is less than equals to the summation I is equals to 1 to infinity the measure of ei. It is what basically the countable subadditivity. This property is known as the countable subadditivity. The countable subadditivity. And if ei's are basically ei's are pairwise disjoint, if it is pairwise disjoint, then the outer then the measure of I is equals to 1 to infinity of union ei is basically the equal. If it is a pairwise disjoint, then this inequality will be the equality, and it is known as the countable additivity. So now, how can we prove these results? So we'll have some properties. So we'll start with that property only. So start with the proof. Since the set ei from I is equals to 1 to infinite are measurable, then so the union of all measurable set is also measurable. So the union of all measurable set is also measurable. It means the measure of union I is equals to 1 to infinite of ei is what is equals to the outer measure. Okay, the measure is basically the outer measure. It is a union I is equals to 1 to infinity of of ei is less than equal the summation of I is equals to 1 to infinite the outer measure of ei. This is the result that we have, and it is also less than summation I is equals to 1 to infinite the measure of ei. Okay. Now for first part, this proves, this is the thing that we have the measure of union I is equals to 1 to infinity I is what? It is less than equal the summation the summation I is equals to 1 to infinity of m of ie. It is what? The part 1. Hence prove the part 1 that we have proved by this result only. All measurable set is all union of all measurable set is union. Now we'll try to prove the equality in the same. So if all ei are pairwise disjoint, pairwise disjoint measurable set, then for each pair, or sorry, for each positive integer, or for each positive integer, or basically the pairs are e1, e2, e3 up to en are measurable. It means these all are pairwise measurable. It means for all positive integer 1, 2, 3, 4, it is also measurable sets. So these are measurable sets. So let A be any set of real number that is outer measure of A intersection with the union I is equals to 1 to n of ei. This is what? This is the measurable set, and the intersection with A is nothing but the summation is equals to the summation I is equals to 1 to n is outer measure of A intersection E I. So now in particular case, this is the property. Okay, so in particular that what we have, that basically R A is basically the R. If it is a real number, set of real number, then the outer measure with R, the intersection of basically union I is equals to n. It means this A is basically what? R, and it is I, okay, is equals to the summation I is equals to 1 to n is what? The outer measure with R intersection EI. Okay, now similarly we can write the outer measure is union I is equals to 1 to n, it is what? EI. If it is R, then union with R, it is what? That we can write in this sense. Is this basically equals to the summation I is equals to 1 to n is the outer measure, the R with E, because E is a subset of R, then the intersection is what? Because EI is the subset of R, then we can write it as just E. This is what? The equation number 1. Now, next. Yeah, I think this is what we are going to prove. Next. Outer measure, yeah. Yes. We want the measure here. Okay, it is for outer measure only. Now we'll do the same in the similar manner. Yeah, here we need M only. Okay, the measure, the outer measure is basically the measure only. Next, if we can write, if we have this, then M is Lebesgue finitely additive. So if it is a finitely additive Lebesgue, then let now the union I is equals to 1 to infinite E. What we want to do basically, this outer measure should be the measure only. Okay, this outer measure should be the measure. So we'll just prove it by the equality case. First we will prove it is less than, and we'll put it is greater than. So it will be equal for the measure. Okay, what is the measure? When outer measure and inner measure, outer measure and inner measure are equal, then it is a measurable set. Okay, then the union of I is basically what? Is a superset of ui is equals to 1 to n of all ei. Okay, basically it is a 1 to infinite. It is basically the superset, or basically this is the subset for this, for every n belongs to the natural number. It means it is a finitely additive. It is a finitely additive. Yeah, Lebesgue is finitely additive. So now we have, we'll take the outer measure for both this. So we'll take just outer measure, then we'll get I is equals to 1 to infinity of all ei. If it is a superset, then it is a greater than equal. Then m star of union I is equals to 1 to n. Okay, it is 1 to n of this is what ei. So this is the equation number 2. Now, if it is equation number 2, then if it is greater than, it means there is an inequality in this, in such a case, then we can write for this m star, it is what, 1 to infinity, na? So it is ei is greater than, it is also greater than for only one of e, only one of ei. So it is the equation number, you can put, yeah, it is the equation number 2 only. Now, in the limiting case, when n tending to infinite, what will be, like, what will happen for this? If n tending to infinite, yeah, it is basically the limiting case. The limiting case, n tending to infinite, this what we'll get, the m star is what this. So in the limiting case, this outer measure will be the measurable for this. It means for limiting case, that what the property is here, it will be the measure of I is equals to 1 to infinite of all ei greater than equal is basically the summation of I is equals to 1 to infinite is m of ei. Now, earlierly for the equation number 1, what we have done, this thing is less than. So I say it is my A and it is what B. If it is V, then by A and B, then by equation A and B. This transformation is just because the limiting case and the property that we can write the outer measure in terms of summation. So basically the union of outer measure is in terms of summation. So it is what that we can write in such a way that if it is greater than here, and here in this case it is less than, it means that these both equations are just A is greater than B and A is less than B. It means it indicates that A is equals to B. So it is nothing but m of ui is equals to 1 to infinite of ei is what equals to the summation of I 1 to infinite of m of I. So this is the property that we just desire to prove these properties. So this is the property. So this is called the countable additivity and this is called the countable subadditivity. So this is the property. I hope you are getting this property and you are, yeah, you are getting the property and you are getting the concept of the Lebesgue measurable set. So thanks for watching my video. Keep watching MS Maths. For more videos, you can subscribe my channel. Thank you. Bye bye.